Hi, college algebra student. This video is for chapter 6.1, exponential function. When we think about or heard about this exponential word, you must have heard that, oh, something's grow exponentially. So it's shoot up really quickly. So that's what our feeling is. So obviously, if something shoot up, like increase exponentially, we cannot use a line to model it. So there is exponential function that can model it. So technically speaking, what is an exponential function? Okay, it turns out that exponential function, so according to the definition that is documented here, that the function y value has a same constant percentage change. That means your change over the percentage that you add to it is constant, or you have a same multiplicative factor, or you're multiplying the same number over the same increment. So when x increase the same, you multiply the same number, or you increase the same percentage. The multiplicative factor, the growth factor, is easier to detect than the percentage factor, but they are equivalent. Linear function is same, but not same percentage, same amongst change. So you add the same number. You add the same number. For exponential, you multiply the same number. So we'll illustrate this by looking at this four function. They all have a same incremental increase in x. So add 1, add 1, add 1, right? And all the x's add 1. But y, you can see that for the first one, f of x, it increased 5 to 10. So from one increment, you add 5. Y, this would add 5. And this is also add 5. So this is linear. You have a constant change. It's constant change, constant rate of change, because 5 over 1 is constant. Let's look at this. This seems to increase. So let's look at the increase. So this add 3. Oh, this add 4. A little bit more. Oh, but then this add 1. So obviously it's not linear, but is it exponential? So let's look at the multiplicative. If I compare 5 and 8, how much do I multiply to get from 5 to 8? So you can think of this investigating plus, you can investigate multiply. For multiplying, you would divide 8 divided by 5. So you multiply 1.6, because 8 over 5 is 1.6. So what do you multiply from 8 to 12? So you would say 12 divided by 8. Oh no, 12 divided by 8. That is multiply 1.5. It is not a constant multiplication, right? And from 13 to 13, you multiply by 13 over 12. This 1.0. So neither, right? It's neither exponential nor linear. If it is an exponential, you multiply by the same number. Let's look at this too. So this look like exponential. So you start from 2, and then after 4 rounds, wow, it shoot up to 250. Let's look at. So let's just do add first. Of course, it's not going to be constant, because this would be adding 8. This already at 40. So it's not going to be constant. So this add, right, 200, right? So not linear. For multiplying, so from 2, how do I get to 5? I multiply by 5, right? How do I know? Because I do 10 divided by 2, so it will be 5. 15 divided by 10, multiplied by 5. 200 divided by 50 is multiplied by 5. You can see that it has the same multiplicative factor. The growth factor is constant. We call it factor because factor is about multiplying. It's a constant. So it is exponential. Same multiplicative factor, or we call it growth factor because it's increasing. Let's look at this. This seems to be decreasing. So from the addition point of view, is decreasing by a negative number. So negative 150, right? Decrease by 60, so it's not constant. Decrease by what? 20? Is it 24? 24. So not linear. Not linear. So if it is a linear, it could decrease the same amount. Let's look at multiplication. So how do I know what multiplied 250 to 100? So we can do 100 divided by 250. Oh, it is actually multiplied by 0.4. So remember, you do 100 divided by 250. Your answer, so because you're investigating 250 multiplied by what? You go to 100. So this number would be divided 250 on both sides. So that's how you do. So that's 0.4. What about 40 divided by 100? Of course, that's 0.4. And this is also 0.4. 16 divided by 40 is 0.4. So they multiply the same number. It's not a negative number, but you multiply a fixed number. So constant factor, growth. It is not a growth. We call it decay factor. But it is a same decay factor. It's the same number, so it is still exponential. This is called the exponential decay function. And this is exponential growth function because of growing. This is decreasing, but both of them you see are multiplying a number. This multiplied by 5 in every single increment. This multiplied by a fraction, 0.4, in every single one. So that's how we distinguish them from data. If you look at the graph, if you don't want to do this multiplication, you can actually graph them on decimal. So let's look at decimal. Switch to here. Right over here. So I have entered those 4 tables here. So let's look at the first one. Zoom in. Yeah, I think I'm gonna. They're all mixed together. So the first one, can I zoom in just for the first one? Yes, it is obviously linear, right? So the first one is linear. By looking at it is a line. So I'm gonna do the second one, and the second one, zoom in. It's not exactly a line, so it is neither. But it is also not growing or decreasing. So it's neither, so we off it. The third one is the one that we say multiply by 5. So let's look at the whole thing. So it is, if I draw on it, I don't know if I can draw on it because there's nothing I can draw on. So you can see that it is like that. Okay, you can see it is growing fast. It's exponential growth. Okay, exponential growth are like that. And then for the fourth one, it is an exponential decay. So it would start off decreasing, but then actually for exponential decay, they don't decay sharply. It would actually slow down. So in such a way that it's not going to cut through 0. It would just be decay, decay, decay like that. Okay. So this is how you analyze exponential. So they have special graph. So the graph that you will see actually just two types. So let's go back to this one. Oops, so not this. Those. The graph you will see would be, so we say the last 2 are, right? So if I graph it on decimal, this look like, for growth, it look like something like that. Okay. And then the other one, this is the decay. It look like something like. So in either case, it's at the for growth at the growth positive side, it shoot up to infinity, but on the negative side, it never drop down. It would slow. It would have a horizontal asymptote. For the decay one, it would have a horizontal asymptote, and it would shoot up on the left-hand side. So this is the two behavior of an exponential function. What about in a formula? So we look at data, we look at graph. Let's look at how exponential function behave as a formula. So we say exponential function always have a constant as a base. It involves exponent, right? So it would have a constant base and a variable exponent. Let's look at this. 4 is the base. 3x minus 2 is exponent, and that's where our variable is. So this is an exponential function. The second one, h of x 1/2 is a constant. It's just a number. X is a variable, so this is exponential. -2, oh, -2 is a constant, but it's not positive. It has to have a constant base. I should add it's a positive constant base. The problem of negative base is you would be switching back and forth, right? When you have an even power, it's switch positive, negative, so it's not a like very good function to work with. So this is not because it's negative. Negative base doesn't work. How about the last one? We have a exponent, but the base is not a constant, so this is not. This is actually polynomial. The base is a variable. The constant is fixed. So remember, exponential function in terms of formula is always have a constant base, positive. It can be a fraction, but it has to be positive. And then your variable x is in the exponent. So the most general one that you have would be a general exponential function that can be used to model anything, just like for linear versus linear equal to y equal to mx plus b, right? That's linear. Any line would be in this form. Our corresponding one is f of x equal to abx, ab to the power x. So how do I interpret this? The base is not ab, the base is the b. The a is a constant multiple outside of it, and it's called the initial value. So that means when x is 0, then f of x is b. Initial means when x is 0, f of x is a. It's not b, it's a. Okay. And b is the base, is any positive real number except 1. It doesn't make sense to have 1, right? Because 1 to the anything is 1. And then how do I know whether it is growth or decay? So the function would be a times b to the x. If b is greater than 1, like the one that we have earlier, we multiply by 5. That actually is the base. The growth factor is the base. Then it's a growth function. And if our base, when we multiply, the constant factor is less than 1 but greater than 0, then it's a decay function. So for example, f of x equal to 2 times 5 to the x. So 5 to the x is a growth factor of 5 every time, and this is initial. So this would model this. Good. Oh no, 2 is not initial, 0 is initial. So yeah, that doesn't model it. But in case you have a function like this, when x is 0, you have 2. And when x is 1, you have 2 times 5. Yeah, so this would be like that. Another function that is, this would be like we can say 100 and then 0.4 to the x. So this would be a decay function. In the beginning, it is 100, and then it decreases by 0.4, 0.4 every time. So as a formula, you see f of x equal to abx is an exponential function. If b is greater than 1, it's growing. If b is less than 1, like 0.4, then it is decaying. What about domain and range and everything? So we say domain is domain is always a real number because you can put anything in the exponent. And range is positive if a is positive. Range is negative if a is negative. The y-intercept, if I am to graph y equal to abx, like for example a is positive, this would be a. The y-intercept is also a because it's a times 1, because it's, well, a times b to the 0. B to the 0 is 1, so that's why it's 0a. And then there is a asymptote. That means they doesn't drop below. It always approaches 0. It's y equal to 0. Okay, so I'll quickly go over. So is it a growth? We only look at this. This is a growth because 1.1 is greater than 1, so growth. Growth exponential. This is 0.11 is less than 1, so it is decay. 0.11 less than 1 decay. What about this? 1.06. Oh, but this is not a x. It's 1 over something. It's neither. It has to be just to the power x. Okay, so that's how you recognize exponential function from data, from graph, and also from formula.